Hi Year 11, in this video we are going to look at the chemical analysis topic of chromatography, and this is a required practical. Before we do that though, we're going to talk a little bit about purity and formulations before we then look at the chromatography required practical and what sorts of questions you then get asked about it. This booklet is in the booklet you picked up from myself before we broke up for the half-term holidays. So we'll start and we'll go through it now. So we'll start with purity. So it is important you're able to identify substances that are pure, and they come in all different shapes and sizes. These are actually three diagrams of three pure substances, because the word pure essentially means, especially in chemistry, it means one compound or element. Okay, nothing is mixed in. Okay, so nothing's mixed in. So you can see I've got one type of atom here. I've got a molecule here. That could be, for example, oxygen gas. And I've got a compound here, but they're both the same compound. So therefore, that's why it can in fact be deemed as pure. Now, why is that important? Well, purity can link to boiling point and melting point, because a chemically pure substance will melt or boil at a specific temperature. So we'll write that down. A chemically pure substance will melt / boil at a specific temperature. Okay, and that could be, for example, water. We know the boiling point of water is 100 degrees Celsius. And if we add impurities to that, so more than one type of compound or element, so the substances become impure, then that does in fact affect the melting point and boiling point. So impurities in a sample, for example, hey, that rhymes, will lower the melting point. Okay, so it will lower the melting point. So that, for example, would be if you think about adding salt to water, it can change the melting point and boiling points if you're gritting the roads, for example. But they can also increase the boiling point. Okay, so what am I trying to say with this? So basically, the closer to pure you have or you are, then the purer your sample will be. So when I'm saying the closer to pure, what I mean is the closest to the boiling point. So I know, for example, the boiling point of water is 100 degrees Celsius. If I then had sample A and sample B, and their boiling point was 105 and 127, then this would be closer to that. So therefore, I would say this has less impurities than what this substance here does. Okay, so the purer your sample will be. Okay, and you might get a data question on that. You might be asked to identify what substances are pure and impure based on things like the boiling point. So it's just mindful to know how that affects boiling and melting points. What we then went on to look at with you was formulations, and being able to define what that word actually means. And if you remember in lessons we talked about, if you went abroad and you went and got a piece of chocolate like a Twix here, would it still taste like a Twix? And the answer is yes, even though it is sunny and probably does taste a little bit better. It will taste the same because these are all examples of formulations. So formulation, okay, are useful mixtures with a precise purpose. That's the textbook definition of it. Okay, and they're made by using a formula. And that's where the word formula comes from. You can see the words in the actual name. So substances that have essentially got fixed quantities. And we went through this with you in the lesson and we gave you lots of different examples. So paints, for example, are good examples of formulations. You've got cleaning products, like bleach, for example, fuels, and you've also got fertilizers. So you're often asked what would be the chemical name given to this substance. When it's that type of question, be thinking, is it a formulation? Does it have fixed quantities in it? Is it a mixture with a specific purpose? You can also see that it links to fuels, which is a paper 2 topic, and also fertilizers, which links to NPK fertilizers. So it's just being mindful that formulations can then link to other topics. So we're now going to look at the required practical, which is chromatography. This was on the foundation tier paper last year as a 4 marker, if I remember right, and it was not on the higher tier paper. So it's a good chance that this potential area will come up as one of the required practicals. So essentially what we're going to do is we're going to go through the methods, so that almost, as you call it, the 6 marker type questions you get on this. And then we'll talk a little bit about the calculation and the other types of data questions you might get around this. So diagram's not very good, but I'll try and re-sketch over it. You can see I've got my chromatogram here. I've got a substance that goes to there, start line's there. I've got 3 substances and I've got another line there like that. Okay, and essentially we're going to mark out how we would do this particular thing. So the first thing I want you to be aware of is this is an analytical method. So it is a way of separating substances in a mixture. Been a long day. Separating substances in a mixture. Okay, and we can do that. It's usually things like ink or dye. And we can do that following this particular method. So the first thing we want to do with this is get our filter paper and draw a start line. And you want that to be slightly above the size of the filter paper. So you draw your start line and it has to be drawn in pencil. And that is often a question you're asked. Why? Why is it drawn in pencil? Well, that's because pencils are insoluble. So in other words, they're not going to dissolve into the solvent and move up through the filter paper. They're going to stay where they are, okay? And that's the first thing you're going to point out to the examiner. What I then do is add my mixture as a spot, okay, on the start line, okay? And then place that into my beaker with a solvent in it. Into my solvent. Now, the important thing you need to remember about that is the start line has to be just above the solvent line. Guess what they ask? Why? Okay. That's to make sure the ink moves up through the filter paper rather than dissolving into the solution. Okay, so that's the reason why you want to make sure that you put that on the start line. What I do want to point out is the solvent could be water or it might be an alcohol like ethanol. It's a substance that has the power to dissolve, which is why sometimes you're asked about placing a lid on top of the beaker, and you can see that on the picture I've given you. So place a lid on the top of the beaker or container, and that is basically to stop the solvent. If it was ethanol, for example, it would evaporate to stop the solvent escaping through evaporation. Okay. Then what we'll do, what I noticed when I was marking the 4 marker and the PPEs was that people would then stop there. They wouldn't then explain the fact that you'd allow the inks to move up the paper until it reached the top slightly. You then take the chromatography paper out of the solvent, leave to dry, and then analyse. And that was the bit people forgot to include. So it's important that you do say that. What I do also want to highlight is, so essentially the dyes will move up the paper. If it doesn't move up the paper, then we could actually say it's insoluble. Again, could be a question you could get asked about that. And they will separate out based on their solubility. The further up the paper it goes, the more soluble it is. So it is important that you know that. So when the solvent reaches near the top, I mean, it could be the solvent or the dyes, reach near the top, you're then going to remove and allow to dry. At that point, you can then analyse your chromatogram. So you might be, for example, asked to calculate the RF value, write a conclusion about it. But these are the key things you need to be mentioning. And as I said, steps 4, step 5, that was something that wasn't included. So it's important that you do, in fact, include that. Now, the required practical does have certain terminology around it that you just need to be aware of. So there are 2 phases, for example, within chromatography. We've got the mobile phase and the stationary phase, and you need to be able to identify examples of both of those and define them. So I think of mobile, I think has the ability to move. So the definition would be where the molecules can move. So that, in the case of chromatography, would be the solvent and the dye moving through the paper. Okay. And the stationary phase, stationary means stop, does not move. So the only part of the equipment that does not move physically is the filter paper. So where the molecules can't move. And actually the dyes get to that point, they get to the stationary phase. So if you think about my chromatogram, there's my start line, there's my dye. The solvent moves up through the filter paper, taking the dye with it. The dye separates out based upon solubility. When it comes out and stays there, that's when it then reaches the stationary phase. So what I'm trying to say by that is that you do in fact find the things move between the phases, and they do move in between them. But typical questions are ticky boxy ones where you could be matching up the phase to the definition. Know that the mobile phase is the solvent, the stationary phase is usually the filter paper. So what I thought we'd do is look at some exam questions on this just to see the types of questions you get asked. So again, stop the video, bug the question, give it a go. So chromatography can be used to separate out components of a mixture. I shouldn't use paper chromatography to analyse black food colouring dye. So they're analysing that. That's my mixture. They shouldn't place spots of known food colours A, B, C, D and E and the black food colouring on the sheet of chromatography paper, and they shouldn't set up apparatus, fancy word for equipment, as the diagram below. I've got my lids, I've got my chromatography paper, my solvent, I've drawn my line, my start line in ink and my black food colouring. So already I can see there's mistakes there. So the student has made 2 errors in setting up the equipment, identify what the 2 errors are and describe the problem it would cause. So I'm hoping straight away you can see that the start line was drawn in ink. So I'm going to tell them what the error is. Start line drawn in ink. Describe the problem. This will dissolve in the solvent. Should be drawn in pencil. Okay, and the second one, well, we can see the solvent is actually here and the start line is below the solvent. So start line is below the solvent. which means it will, in fact, the inks will dissolve into the solvent. And as such, they will not move up through the paper. So you might get asked questions about spotting mistakes if you've not got a 6 marker, being able to write a method. It could be a sort of looking at the methods and breaking down mistakes that have been made. Or you get asked about forming conclusions from chromatograms. For some reason, students seem to leave these blank, and yet they're usually 3-mark questions, and they're usually dead easy to pick up marks here. So the first thing I'm going to say is say what you see, okay? If you've got 1 dot, then that means you've got something that is pure, okay? So C, for example, I would say is a pure substance. If you've got more than 1 dot, like X, you can see I've got 2 dots there, then I'm going to say that that is a mixture. So if this was a 3-mark question, I've already picked up 2 marks. What you're always going to have to do when writing conclusions from chromatograms is, do they match to anything else along the chromatogram? So as you can see, X contains A and B. So again, if I was writing a conclusion, if it's something that's along the same lines, then I can say it does in fact contain this. So X contains substances A and B. Okay. Other types of things you might want to mention here. Essentially, if it doesn't move, if you don't form a dot, for example, so in D you can see I do not have a dot there at all, then that tells me the substance must be insoluble. Remember, the further up the substance goes, the more soluble it is. So further up the filter paper, the more soluble the substance would be. So these are really questions that you shouldn't leave blank. So I could also say X does not contain any C or D. So there's lots of conclusions you can in fact write about a chromatogram. The key thing is saying what you see happening. The last thing we're going to talk about when it comes to chromatography is the RF calculations. And it is important to point out that foundation tier paper, you're often given this calculation. Higher tier paper, you're not. You're expected to know it. So it is important you're able to do this. What I will say is it's relatively straightforward to do, but you need a ruler. So you need to make sure you've got a ruler and access to a ruler in your exam. You can see you've got your baseline, you've got what's called the solvent front. And as you can see from my arrows, if I was trying to work out the RF value of this dot here, then I'm going to outline to you what I would do. So the calculation is quite straightforward. It's the distance moved by the substance divided by the distance moved by the solvent. So to work out which is which, the first thing I'm going to say is that there, you would start on your start line and go up to about middle part of the actual dot itself, and that's the distance you would measure. And that's why that number there would be in millimeters and would be smaller than the top number, the bottom number, should I say. So I'd get my ruler from the baseline, from the start line, draw it up to the middle part and measure that distance in millimeters. Okay, that's going to give me my number for the top part of my equation. The distance moved by the solvent, well, it's often called the solvent front, and it will always be labelled on chromatograms. So you can see my solvent front is there. So again, I'm measuring from the start line up to the solvent front using my ruler, making sure I'm in the right units there, which is millimeters. So A would be the bottom part of that reaction. Let me just tell you now that RF values are always below 1. So if you do the calculation the wrong way around, you will not get an answer below 1. So that will obviously prompt you to figure out you've got to turn them the other way around. RF values are always below 1. Okay. Depending on the solvent you're using, that will change the RF value because each solvent can dissolve things in different ways. You might be asked to rearrange that equation. So they might ask you, so you got the solvent distance, the substance distance divided by the solvent distance is what gives you your RF value. They might ask you to calculate the solvent distance. You're essentially putting it into the triangle and rearranging the triangle. It's not as complicated as the calculations on paper one. It's relatively straightforward. But the key is having a ruler. The key is making sure we know that the smaller number goes on top and we're dividing it by the bigger number, which is the solvent front. You want to measure up to the middle part of the dot, and remember that the RF value is always below 1. So we'll look at some examples of this. So here's an exam question where we've got a question about ink. The student investigated green ink using paper chromatography in a beaker. The diagram below shows the results that the student obtained. The measurements A, B, C, and D the student could make. The student calculated the RF value of the blue dye, okay, and the student measured the distance moved by the blue dye to be 2.7 centimetres. The distance moved by the solvent to be 9. Calculate the RF value. So you can see they've given me the calculation there. So the distance moved by the dye would be 2.7 in terms of calculations. And I'm dividing that by the distance by the solvent, which would be 9. And that's then going to give me my answer for the RF value. I've not got a calculator on me just now, but that's essentially what you would do. Next question again, very similar. You can see this time though, they haven't given us the actual calculation. So I need to know what the calculation is for this. So we've got the RF value. So the student investigated green ink using paper chromatography in a beaker. Okay. Use water as a solvent. Here's the chromatogram they obtained. The RF value of the yellow dye is 0.60. So again, I'm thinking about my triangle. RF value, solvent front distance, substance distance. The distance moved by the yellow dye was 5.7 centimetres. Calculate the distance moved by the solvent. Okay. Now, depending on the number of marks, which I don't seem to have here, I might have to convert that units, but we're just going to use the numbers that they've given us for today. So I know that to calculate the solvent, I am going to do this distance moved by the substance divided by the RF value. So the distance moved by the substance is 5.7, and I'm dividing that by 0.6, and that would give me a distance of 9.5 centimetres. Okay, so that is that topic there, chromatography. Again, as always, if you've got any questions, don't hesitate to ask, and I will hopefully get to see you soon. All right, take care, everyone.